Sills. All I really need to know, I learned from Dr. Z.
Thank you. Thank you very much. It's great to be back at Rutgers. I think this is the first time I'm back on campus since I left. So I spent 4 years here as an undergraduate, and then later on 4 wonderful years as a postdoc, working under Doron's mentorship, and it was wonderful, and thank you so much, Doron. I want to echo the sentiments of some of the previous speakers and add to the list. So not only is Doron kind and generous to a fault with undergraduate students and his graduate students and Richard Stanley's graduate students, but also to his postdocs, so thank you. Okay, so this of course is a parody title, as you probably recognize, but I mean it seriously in a way. I'm going to make references throughout the talk to different ways that Doron has influenced me and influences my way I approach research and teaching and, I guess, wardrobe at conferences and things like that. So, okay, so first of all, I have to apologize to Doron because I do honor opinion number 60 in principle, but there isn't enough time. So to make amends for that, I also read opinion number 106, so the fonts will be large. And perhaps even more importantly, Doron in opinion number 104 was kind of, I guess, bemoaning the fact that we as a profession have become so overly specialized in our specialties that we need more generalists and that sort of thing. So while I can't claim to fully honor this, I'm at least going to go out on a limb here and step out of my comfort zone of Q-series and partitions and talk about something that I know very little about. So how did this come about? Well, this is joint work with my colleague and friend and now collaborator at Georgia Southern University, Hua Wang, who works, among other things, in combinatorics and chemical graph theory. So this is we're going to be talking about chemical graph theory today. So first, just a few standard definitions. As always, a tree is a connected graph with no cycles. The degree of a vertex is the number of edges that are incident to the vertex. A leaf is a vertex of degree 1. Here's a terminology that I had a little bit of a problem with, a degree sequence. This is not really a sequence, is it? I mean, it's a multi-set, right? Because basically, if you have your vertices V1 through Vn, and you write down what the degrees of each of them are, how do you get the degree sequence? Well, you take them out of order and you put them from largest to smallest. So, and that's going to create a little bit of awkwardness in terms of something that's going to come up later. But anyway, I got my rant about that out of the way now. And also, all my trees will have n vertices and k vertices of degree.
So you're talking about unlabeled trees, I guess, not labeled trees.
Right.
Because for labeled trees, it's the sequence.
Yeah. So. Anyway, so I have to introduce something called the Wiener index, which I had never heard of until, I guess, April, when Block told me what this was. So, I mean, there's an official definition, but basically what it is you've got n vertices in your tree, and you take every possible pair, and you count how many edges there are between them, and add them all up. So that's the Wiener index of a graph. So following Doron, you teach by example, so I'll give you an example in a second, but I just want to mention historically, this was introduced by Harry Wiener. He, of course, didn't call it the Wiener index, he called it the path number, but he called it in his paper W. For no particular reason. So I don't know, I don't know the cursor of WZ going on there. And this was apparently a groundbreaking paper, and this is used by chemists. And also, he was really 19 years old when he came up with the idea for this, and published it when he was in his early 20s. So anyway, the problem that I want to talk about is among all trees with a given degree sequence, in the sense I talked about, so we've got the decreasing here, and we've got n minus k leaves, we want to find the one or ones that have the maximal Wiener index. So for example, if we have the degree sequence 3, 2, 2, 1, 1, 1, here's a tree that has that, and here's another tree. They're different. We've got, in terms of actual sequence, as opposed to this kind of sequence, 2, 3, 2, and 3, 2, 2. Well, the one on the left has Wiener index 31, and the one on the right has a Wiener index 32. So is there a way that we could have predicted that this one would be better than that one in terms of higher Wiener index? So that's the problem that we're interested in. And also, there's a neat formula for the Wiener index, apart from the definition that I just put up before, that I'm going to show you. So it's actually going to be easier if I change my d's to what I'm calling b's, which is basically I'm going to subtract 1 from the degree in each of these. The formula depends on something that is always 1 less than the degree. So my d1 equals 3 is going to become a b1 equals 2, the d2 equals 2, is going to be, and so on. So I've got that on the next slide. And then the leaves don't affect the formula at all. They would contribute 0, so I didn't bother writing them. Also, I should mention a caterpillar is a special type of tree where there's a central path called the spine S. Every edge is either contained in that spine or it's incident to it. And there's a theorem due to, I don't know who, and I should have looked this up beforehand, but I didn't, I'm sorry. If a tree has a maximal Wiener index for a given degree sequence, then it has to be a caterpillar. So you only have to look for caterpillars. Okay, so here's the formula. The other way you can calculate the Wiener index. It's got, where n again is the number of vertices it knows. It's n minus 1 squared in it, and then it's got this sum. So as you can see, there's this 1 being subtracted from the degree. So here, this is what I would actually call a degree sequence, right? You've got vertices, non-leaf vertices, v1 through vk, and in that order, this is the degrees. Okay, and so once again, we don't really want to, it'll be simpler to not have this shift by 1 in there, so I'm going to change my z's out for these shifted y's. So what we want to do then is find a permutation for a given degree sequence, b1 through bk through bn. We want to find a permutation, which are the y's, that makes this sum as big as possible. So I'm going to, since the n minus 1 squared is fixed, we have to pay attention to the sum. So I'm going to call this sum capital F, and then I'll call something else later when I give you some other notation. So a priori, of course, you've got k factorial possible candidates, k factorial permutations. Well, right away we can cut that in half because of the symmetry in the sum, or I guess the symmetry in the graph, the spine. You can read it forwards or backwards. You get duplicates of everything. So you get k factorial over 2. Turns out you can do a lot better than that using another theorem, which I will not write out, but I will just demonstrate by example at k equals 5. Again, it'll be a lot clearer. This is something I learned from Dr. Z. So basically, for k equals 5, we want to, b1 is always y1. And then there's only 2 possibilities for where b2 can go. So in other words, you've got your y2 through y5 slot have to be filled out. Well, it can only go to the far left or the far